Today's lesson is on exploring solids. Similar to when we first got into like quadrilaterals, we kind of talked about polygons. Well, now we're going over three-dimensional figures as that is a focus in chapter 12. So first off, we've got the term polyhedron. It is basically a polygon in 3 dimensions, right? So it is a solid that is bounded by polygons, so we don't have curved faces. Just a little note that face is kind of our 2-dimensional plane, vertex is a point, and edge is kind of the line, right? And in this case, a face over here was connected by 4 edges, or drawn by 4 edges, I should say. Vertex is going to be where 3 or more edges meet. We've got a couple different types of solids here. We've got prisms, and pyramids are polyhedra, where they're made out of only kind of non-rounded shapes, whereas we have cylinder, cone, and spheres are not considered polyhedra. So a couple different notes here. For prisms, they're identified by their base, right? So we might look and see a lot of rectangles, but the key difference here is we have this pentagon on top and bottom, and so this is considered a pentagonal prism or pentagonal prism, right? And again, the 2 bases of the prism are congruent polygons in parallel planes, okay? This one would be a triangular pyramid because we look at the bottom, like if this is our apex of the pyramid, the bottom is a triangle. We could have a square, a rectangle, a pentagon, hexagon, so on, right? So starting off real basic, tell whether the solid is a polyhedron or not, and classify it and identify the number of faces, vertices, and edges. So looking at this one, I only see flat, right? I only see flat edges. I don't see any curves. So this is, yes, going to be a polyhedron. In this case, I'm counting our faces. We've got the bottom is a hexagon, and then we've got 1, 2, 3, 4, 5, 6 other faces leading up to the point. So we have a total of 7 faces. Now, just as a note, I classify it first. This is a pyramid, but its base is a hexagon. So this is a hexagonal pyramid. Next, we're doing vertices. Faces, vertices, edges. So vertices are how many basically little points we have here. So 1, 2, 3, 4, 5, 6, and then they all meet up at the top at 7. Lastly, edges. We've got 1, 2, 3, 4, 5, 6 form the bottom, and then we'll kind of start back here. 7, 8, 9, 10, 11, 12 edges, right? Used to draw that. So E for edges equals 12. Next one, this picture looks like a cone, so it is not a polyhedron, so we won't identify number of faces, vertices, edges, right? That's specific to a polyhedron. Next one, we've got, looks to be a parallelogram, but I see a right angle, so that's going to make this a rectangular prism. Sorry, it looks like it's supposed to be rectangular prism here. Erase some of that, make it look like a C, but rectangular prism is what we've got here. And then how many faces we have? We have front and back, and then top, right, bottom, left. So that counting those is 6. Now, how many vertices do we have? 1, 2, 3, 4 here, 5, 6, 7, 8 there. And then our edges is going to be 4 here in the front, 4 in the back, and 1, 2, 3, 4 lines connecting the 2, or edges, for a total of 12. See a pattern between the faces, vertices, and edges yet? Kind of be looking for that pattern. Next, this looks like an upside down mailbox, maybe a feeding trough. So that one is not a polyhedron. Next one, this looks like a triangular prism. Right, we don't go to a point, so it's not a pyramid. So triangular prism, yes, is a polyhedron. And therefore, now we're counting faces. We've got front and back, and then so 2, 3, 4, 5, like top, bottom, left. So I've got 5 faces, vertices, 1, 2, 3, 4, 5, 6. And then lastly, edges, 1, 2, 3 in the front, 4, 5, 6 between the front and the back, 7, 8, 9. So we got a total of 9 edges. We'll learn a formula in a moment on how these are supposed to be related. So see if you can figure it out before we get there. And then lastly, we've got, I would call it either a square or rectangular. Actually, what we have, we've got, it looks like a rhombus, but we have a right angle, so therefore we know it's a parallelogram. Rectangle rhombus is going to give us a square, so this is a square pyramid. weird as that sounds. Quadrilateral pyramid would also work. I'm not too worried about being specific there. But faces, bottom, left, right, front, and back, I count 5. Vertices, 1, 2, 3, 4 on the bottom, 1 on top for 5. And then we're going to have 8 edges, 1, 2, 3, 4, 5, 6, 7, 8, kind of counterclockwise there. 8 edges. Now, there's a equation called Euler's theorem. It does not look like Euler, but that's actually someone's last name, Euler, and that's how it's pronounced. Much as it looks like Euler, it is Euler. And so he came up with a couple theorems, but this theorem here is that faces, vertices, and edges, right, are related by this formula. Faces plus vertices equals edges plus 2. Kind of looks like fave, F add V equals E plus 2, fave 2. That's kind of a way I like to look at it, or you could look at it as 5, 2, but I kind of look at the adding as either A or a P, but in this case, you know, right? So F plus V minus E equals 2 is another way to think about it if you want them all on one side. And so we're going to use this a couple more times to verify some of the edges, faces, and vertices, pardon me, that we find in some of these later problems to make sure that they match, that they should verify Euler's theorem. So kind of a weird looking one, looks like a bench to me. So find the number of faces, edges, vertices, and then check our answer using Euler's. So faces, I've got front, back, top has 2, so we have front, back 2, 3, 4, front 5, 6, back 7, and bottom 8. I believe I'm counting 8. So one more try. Bottom, the sides 2, 3, 4, 5, and then 6. We want to count that. 7, 8. So I'm counting 8. How many vertices? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then edges. Whew, a lot of edges. Maybe we'll go bottom up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 is what I counted. And so 8 plus 12 equals 18 plus 2. Check. It works. 20 equals 20. And we're good. A couple more of these. Vocab. Right? What is regular? So regular in a two-dimensional figure is all sides are congruent and angles are congruent. A polyhedron is going to be considered regular if just all its faces are congruent regular polygons. Okay. So in this case, we have a regular convex, looks like triangular pyramid. Now over here, this is almost looks like a Minnesota shape per se. But it's a non-regular. We don't have equal marks all over, and these kind of have this concave look, right? So convex is, a polyhedron is convex if any 2 points on its surface can be connected by a segment that lies entirely inside the polyhedron. Kind of like the diagonals idea, but with 3-dimensional. So again, think convex polygons as 3-dimensional, right? Cave, usually we can make a cave. That's typically true. With concave. If a segment goes outside, then the polyhedron is non-convex or concave. Next, we're going to go over some Platonic solids. Okay, Platonic solids are polyhedron that are regular, and they're named after Plato because he figured these out way back in the day. Only 5 of them exist, and these are generally speaking also the different types of dice or die you can have in a game. You could have a 4-sided die. Usually they have the numbers at the top for each point. Whichever point is pointing up is what you rolled, right? For sure, we're familiar with a cube, all squares. We don't need to know these names. This is just pointing them out. Octahedron, 8 sides. We got a dodecahedron, which is 12 faces. Sorry, 8 faces. In regular icosahedron is 20 faces. Moving on, we've got cross section, right? Typically, if we have a plane intersecting through a solid, we'll have the intersection of the two form the cross section. Like in this picture, I kind of see the dotted lines form a triangle here, dotted line, and the rest of this purple part. And so that cross section would be a triangle. So we're going to go through a couple of these, and then we'll wrap it up. So in this picture here, we've got what looks to be a cube, being again cross section here, and it forms this triangle, so that would be a triangle. Over here, a cross section of a plane and a cone gives us a circle. If they went at an angle, they could have given us an oval as well. And this last one, we've got a what appears to be a hexagonal prism. Our cross-section in this example happens to be a hexagon. And that wraps up today's lesson, pretty short. We'll get into surface area and volume through the rest of this chapter.